tutorial. Janakee, are you listening?
Yeah, hi. Uh,
Yeah. So
I'll share
please
my
share the
screen.
screen here. And
And I'm going to be writing on the screen. So please just let me know if something is, not working.
okay, 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 okay. Please go ahead.
Okay. So hello everyone. And I am going to be taking tutorial for this course taught by Professor Shiv Sethi in Cosmic Town. And most of the things I'm going to do today is what he covered in the lecture yesterday. Mostly the epoch of recombination to about the thermal decoupling, and I will discuss the later basically the physics during cosmic dawn tomorrow in tomorrow's lecture, and after that I'll be discussing the different 21 centimeter signal, what you expect from different scenarios of the X-ray heating and Lyman alpha coupling, etc. So today it's just going to be everything before cosmic dawn, and if you have any doubt, just ask right away, like because I'm going to be sharing screen and I expect I'm going to derive things on the screen. I expect you people to also write things if you want and derive things, like you can keep a calculator and you can just do the calculations with me. I'll be providing all the constants and all the values equations that we will need for derivations, and I'm hoping that at least it will, some of you will find it useful for the these derivations and calculations. So first of all, I'll begin with giving the basic constants that we'll be using. So this is from the Planck latest Planck results, and these are the densities for baryons, for matter, for radiations, and this is supposed to be lambda. So this is for the dark energy, the cosmological constant, and together these three make one, and these are the fractions of helium and fractions of hydrogen as a fraction of baryon density, and together they also approximately make one, because in this case we are assuming that the universe is flat, so that's what we only have these three components. And what mostly we will be using are these two quantities. This combination is what is basically observed by Planck, and also this combination is what turns up in most of the equations. So it's more useful to just use these combinations instead of using these values separately and during the equations. And this is the value of megaparsec. So beginning with the first Hubble constant equation, we have this is basically the scale factor A, and we normalize it as A currently now to be 1. And we begin by, say, in here we have this one value of Hubble constant at present. So this is at present. I'm also going to be talking in redshift. So the redshift at present is 0. And we have, this is for the radiations. So radiation density, this is the radiation density parameter, and it increases with redshift as redshift to power 4, and matter density increases as power 3. This is for the curvature, and we assume this to be flat, so we take this to be 0. And this is for the lambda parameter. Now we can, most of the calculations which we will be doing for recombinations and cosmic dawn, and even the end of epoch of reionizations, we have certain conditions fulfilled. So for example, we can see what is the value of these effect of these parameters at various redshift, and we can compare, say for example, the radiations with matter. So we have this, and which gives us, when we compare them, basically we want to find when the effect of both the radiations and the matter is the same. So that turns out to be around this, and which is approximately equal to uh, 3000, redshift 3000, which means this is very large, which is much larger than whatever Z recombination, Z recoupling, that's etc., which we have talked about which even Shiv talked about. The second thing which we will compare is the lambda. So lambda with omega m and this, and we will call it the second equality. And so that turns out to be omega m raised to 1 by 3, which turns out to be around 1.3. So only around redshift 1.3, the dark energy coefficient will dominate. Between this and this, the only thing that dominates is this component, and so we will only be focusing on that component. And so we can write h0, h is equal to h0 uh, times omega m raised to half and 1 plus z raised to 3 by 2. So this is the matter-dominated universe, which approximations that we'll be using everywhere. Uh, then we have the value of this Hubble parameter, which is defined as this value h times 100 kilometer per second per megaparsec. So calculating this value, it turns out to be around 3.24 uh, per second. So this is per second times the h. So h is the unknown, which people have used because this value was not precisely known for over a large part of the history. And so we would use the latest value of h that we have, and the current value is this from the Planck data. There is another values of h turns out to be different if you use not CMB but other approximations. I mean other observations, but we are going to be only using CMB. So this is the h we will be using. Now there is the critical density. So this is the density of the universe at present, and we can define it as this. This comes from the Friedmann equation, and I'll not be using this, but you can derive its value, which is defined as this, and it turns out to be around 10 to power minus 29 h inverse. So there is this h inverse gram per centimeter cube. So everything I'll be using is in CGS unit. Uh, so from this, we can also calculate the number density of particles. So number density of hydrogen at present is the baryon fraction. The no, let's first not derive number density. Let's first derive mass density. So the mass density of hydrogen is going to be the baryon density, which is a fraction of this critical density, and the hydrogen fraction. So this is the hydrogen density, and you can have then hydrogen number density, which is this thing, uh, divided by the mass of hydrogen, which is, mass of proton. And similarly, we can have the helium number density, which we will be using this. So this is mass of helium. Now, this turns out to be around almost just 8% of the total number of particles, baryons, but we will not be using any approximations. We can simply put the numbers which we have. So these are the numbers, and we can calculate the value as a function of this value, which we will be using later. And finally, at large redshift, we don't have to, basically, we might not have completely ionized this. This is for the total hydrogen number density. But if you want to find the hydrogen number density for the neutral hydrogen, then you need to find the neutral fraction, which is given by this, and this is the notation, and the over density times the number density of hydrogen at present, and this is the redshift factor. So the number density increases as z cube. This is this same for helium. Finally, we'll be using two type of, please let me know if anybody has any doubt, or I mean, this is just basic, but still. So we will have basically two type of distances. So first is the co-moving distance, which is basically the distance, say from TE to T0 times C, and this is the scale factor that we had used earlier, TT. So this is the definitions of co-moving distance, and basically if the co-moving distance between 2 points remains constant even with the expansion of the universe, so it's a useful quantity to calculate. But when you want to calculate the exact trace, the so basically, by the way, this can be written as z, that is basically the redshift, and you can write that as time c and h of z. And because z observed is less than z emitted, we can write it as the other way around. So we have this. Now, you also want to trace the path of the photon. So for that, you need to calculate the light travel distance. So what we call is this going to be the light travel distance. This is r and this is gamma. I'm sorry, the writing is not very good here. And for that, the definition is little different, just slightly different. So this is basically you're only tracing the path of the photon. This is the velocity of the photon, and you're simply tracing the path of the photon. And that turns out just one factor different, because there was one factor different here. So that is of z, 1 plus z and dz. So that is the light travel distance. And most of the things which we'll be using for, like say for example, calculating the mean free path or calculating optical depth, etc., we'll be using light travel distance, because we will be tracing the path of the photon. But when we want to, say for example, calculate the distance between two sources, etc., then this is a more useful quantity, because this remains constant with the expansion of the universe. Now, okay, so far any questions? I okay, I can't see the chat, so if you have any questions, then simply just ask. Okay.
Yeah, you can unmute yourself anytime and ask. Yeah, please participate in the discussion. Yeah, thank you.
Yeah. Okay. So fine, fine. My screen is fine, right? Now, okay. Just let me stop share and start share again. There is some issue. Okay. Yeah. So now just basic radiative transfer equations. So Shiv today talked about the Einstein coefficients. So these are the three Einstein coefficients: the Einstein B coefficient and Einstein A coefficient. These are the coefficients for any line, which will determine the number of emissions, number of absorptions, and number of stimulated emission also. So the other quantity, which the basic quantity we'll be using, is the specific intensity, and all these notations are from Ribicki and Lightman textbook. So this is the definition of specific intensity. This is the angle averaged intensity, and this is the number density of the particles. So if this is the specific intensity, you average it over the steradian, the solid angle, and over the frequency, and then you divide it by the this factor to get the number density of particles, total number density of particles. This specific intensity has, generally it remains constant as a function of if, with the distance. However, in the expanding universe, it is a function of frequency. So this is the thing that holds in the expanding universe. But in static universe, the in this thing is equal to 0 in absence of medium. When there is medium, it follows this thing. So this is the absorption by the medium, and this is the emission. So most of the thing which we will be using is this factor, that there's mostly just absorption and neutral medium by neutral medium. So you can calculate the how the specific intensity is uh, dropping as a function of distance or as function of tau. Now this is the emission coefficient and absorption coefficient as function of Einstein coefficients, and this is the cross section. So this is an important quantity, that we have different cross sections for as function of different frequency, and this is the line profile function. So we will be taking approximations for most of these things. This is the optical depth, and this is the mean free path. And this is finally the Planck spectra. So for Planck spectra, you have you can take two approximations, and the one which we'll be using, this is for the 21 centimeter signal. 21 centimeter transitions, and this is for, say, for example, Lyman. Obviously, it follows for other these things also, but for the radiations which is important for us, these are the two approximations which we can use. And in case of this Rayleigh-Jeans approximations, you also have you can define this called brightness temperature, which is basically this temperature for the given intensity. Now, finally, let us start the derivations. So, I'll be deriving the Saha ionization equation. This is an equation in which there is a equilibrium between electrons and protons, which is in equilibrium with the hydrogen and photon. This photon is of like 13.6 electron volt, and we want to calculate what is the as a function of temperature, what is the ionization fraction of the medium. So that is what is given by this ionization equation. What is important here is to note that this equation holds when there is equilibrium between these two processes. So let us just first assume that there is equilibrium. In that case, because this is the chemical potential, so the chemical potential for photon is 0, so we have this equation, and the mass difference between electrons plus mass of proton minus the mass of the neutral hydrogen. So here, by the way, this holds neutral hydrogen, and this is for the total hydrogen, which includes also neutral hydrogen plus proton. So the mass difference is the binding energy. And then if the ionization fraction is X, then you can say the number density of electrons is equal to number density of protons is this fraction. And the number density of neutral hydrogen is instead 1 minus X times the total um, number density. Now, this equation, this part is only correct because we are assuming that the universe holds only hydrogen. If there was helium, then you might also have electron contribution from helium, but that fraction is that contribution is very small because the number density of helium is small. So for now we are going to ignore this, and we will see later that this is not important because at the time of helium recombination, because at the time of hydrogen recombination, helium is already recombined, so the number density does not get included from helium. So we have these equations, and finally the degeneracy for electron and proton is 2 because of spin, and the degeneracy of the ground state of neutral hydrogen is 4 because of the hyperfine splitting, which Shiv talked about today. And finally, this is the temperature. So this is which what we had already written, and this is the number density of hydrogen. Now, number density of particles in any state is given by this equation. So this is basically the number density of particles, and we will calculate it in our case, which should turn out to be this. So if you want, you can do this calculation with me. I have written all the useful equations, and let me know if I write something wrong or if something is not the same as what is expected. So basically the number density is going to be G by H square, and this we can expand using this equation. So we have exponent of mu minus mc square minus p square by this, and we can write this as, so this is the approximation that we this is not an approximation, this is correct because in our for our problem. So we will take out the values which are not dependent on p, and we can write equation more neatly. Please let me know if there is any confusion. So this is the mass of the particle, and this is p square dp, and this is the Gaussian integral, so we can just simply write that as this is the answer for the Gaussian integral. And so putting these values, we can get this for the number density of particles. So now these number densities can be same for electrons or hydrogen or proton, etc. And what we want to calculate is basically this ionization fraction. So we can um, calculate this. This is basically, let me just prove that this is number density of electron by the total number density of protons by the total number density, and this factor is the number density of neutral hydrogen by total number density. So then this turns out to be equal to this, what is what I've written. And so we can calculate this for all these values, and just let me please, if you want, you can do these calculations. That would be nice. So for electrons and for protons, divided by the neutral hydrogen, the total hydrogen, which we will keep that as value. And this is for the neutral hydrogen times the rest of the factors. So we have 2 pi kt by h square raised to 3 by 2 times mass of electron, mass of proton, mass of neutral hydrogen raised to 3 by 2. And this one is going to be exponent. This is chemical potential of electron plus chemical potential of proton minus chemical potential for the neutral hydrogen. So this turns out to be 0. But and finally, mass of electron plus mass of proton minus the mass of neutral hydrogen, c square. And this one is equal to basically this binding energy, this one. So this thing, by the way, cancels out because this is 2 into 2 by 4. So this one, this whole factor is 1. So we can write that as 1 by the total hydrogen fraction, and 2 pi kt to 3 by 2. In this one, when we are subtracting the mass of proton and mass of neutral hydrogen, we cannot cancel those two because there is a small gap and it's multiplied by c square, which is basically the binding energy. So it's a large factor. But here we can simply cancel them. So we have electron, mass of electron, and this is the binding energy kT. So this is, we can write that here. And finally, we can do these calculations. We can put in all the values for all these parameters. If you want, I can stop for you to do that. But if you want to do that later, that's also fine. Please let me know if there is any confusion. And finally, we can put x equals 0.5. So then this thing also turns out to be 0.5. So it's basically 0.5, 0.5. And putting all this rest of the values, we get an equation which is a function of z. And we can solve it recursively for z because it's by taking the log of both sides. So I'm not going to do that now, but we can do that. So here I've taken approximation that t is equal to t now plus 1 plus z. So that is how the T is expanded, and this factor comes. The second 1 plus z cube factor comes from NH, which we have used this equation. Please let me know if there is any question. I'll wait. Hello.
Yeah, I don't see any hand either.
Okay.
Like,
So
you can ask a specific question. I don't know whether they are listening.
yeah, that is true. So are you people listening? Tell me if anything, I mean, if this format is not suitable for understanding, if you think this is in this way, things are
Yeah,
not fine, then you can just give feedback on that too. So I'll try to
yeah,
relate.
we expect more yeah active participation in this case. Yeah, please interact. That I can say.
Yeah.
Yeah.
So, okay. Basically, the for the midpoint of reionization, if we assume that the Saha equation is correct, that if the hydrogen recombination
In the
is
chat box, there is a question by Anindita Nundi. Please repeat
okay,
the x power 2 by 1 minus x step.
can you repeat the question? 2 power
Um 2 by 1 minus x step.
2 by
Yeah, this one only. She wants to repeat this one. X square by 1 minus x. Yeah, this is it.
oh, okay. So this is just this one, no? This one, right? So this is just we want to calculate the approximate redshifts. Okay, basically what we have here is this is a very generic function. This is just general function which you can use for any case. This is for the ionization equation. And now we want to apply this for the expanding universe. So in expanding universe, this case holds that the temperature is this function, and we want to calculate the approximate redshift when the reionization has reached halfway. So for that we take x equals zero point 0.5, that is when the reionization has reached halfway, and so this factor is equal to zero point 0.5, and then now instead of writing nh separately and t separately, you can write everything as a function of redshift. So we can write everything as a function of redshift, and you get this redshift factor, two redshift factors. And so now this equation is very specific for just the expanding universe. And we are going to calculate that for the midpoint of reionization. So that's what I'm doing here. Is that okay? Okay. So basically, if you just put in the values of all these things, you'll get two kind of things. So you will have this is going to be log, or you let's not take log. Let's just take this is going to be 0.5 is equal to some factor. This is going to be constant. So the whole of this is going to be constant by this. So some factors x divided by 1 plus z 3 by 2, and this is another factor, so this is y divided by 1 plus z. So if you want to solve it for z, you can take log from both sides, or you can solve it numerically, it's up to you, but you get approximate result the same, which is basically that for zero point 0.5 x equals zero point 0.5, you get z equals around 1360 approximate, when you are assuming that there is only hydrogen in the universe, which means that this one is equal to 1, not 0.75. Is that fine? Mm. Hello? Okay.
Yeah, I hope so. Yeah.
So now you can do similar exercise also for helium, that you can calculate instead of using this hydrogen binding energy, you can use the binding energy of say the second excited state of the helium to calculate the first, second excite recombination of the helium. Okay, to calculate the first recombination of helium, you'll use this energy, which is basically the energy between helium, this thing, to helium, this. So this is the binding energy you can use to calculate the first recombination of helium. So you have to modify this parameter accordingly. And I think if you do this exercise, you should do it for both helium, first excitation of helium, and the second first recombination of helium, and then the second recombination of helium. And for that, you will get approximately redshift equivalent to around 5400 and around 2000. So please do it and let me know if if you can do that, if you can derive that. Okay, fine. Moving on to the recombination. For that, okay, let me know if there are any questions. Otherwise, I'll move on to the combination, which is not done using this ionization equation. This is done using what Shiv has already talked about. This is done using the first excited state. From that, you have two photon transition to the ground state, and then you have Lyman alpha transition to the ground state. So this is 2s state, and this is 2p state. I should have written. So should I move on here? Okay. This is the, okay, so in this case, basically we will be using something called a 3-level atom approximation. And this is the approximate atom that we have. There is a continuum, which is, and this is the first excited state, and we will assume count both of them as together, and as their number density will be counted as summation of both of them. And then there is ground state. So Shiv has talked extensively about the physical processes that take place here and why the direct recombination from the continuum to the ground state does not take place, because the ionization photon which is emitted in this process will be absorbed immediately by the next neutral hydrogen, and the net recombination will be zero. So we will just ignore this process, and we will focus on these processes. From continuum to the first excited state, and from first excited state through two different processes to the ground state. Now we can write the rate of this two photon process is this per second, and the rate of Lyman alpha transition is much larger. It's like 8 orders of magnitude larger than this. However, the problem with Lyman alpha is that it will also, once there is a transition from first excited state to ground state, a Lyman alpha photon will be absorbed, and it will be also absorbed um, right away by another neutral atom, and which means that the Lyman alpha will not cause a complete recombination that easily. It will scatter. It will scatter a number of times, and only when that Lyman alpha redshifts out of the Lyman alpha resonance width, you will have a successful recombination. So instead of this Lyman alpha rate as this, we can write an effective rate of Lyman alpha transition, which is suppressed by the number of scatterings which Lyman alpha has, and we can write that as Lyman alpha by some factor. So this is, let's write that as number of scatterings. So this is suppressed by this factor. And the total rate of transition from the first excited state to the ground state is this plus the effective Lyman alpha transition. And since the degeneracy of Lyman 2p state is 3 times the degeneracy of the 2s state, it will be there will be a factor of 3. So this is the total transition rate from first excited state to the ground state. Okay, keeping this, now we have now we can find the evolution of the number of atoms in the ground state. So if the number of atoms in ground state is n1 and the total number of atoms in the excited state is n2, then we have as a function of the rate of number which are moving in the first excited state is basically this total times the number of atoms in the first excited state minus, and this is the energy difference between these two states. So this is the frequency of Lyman-Alpha transition. Now, if these two states were in Boltzmann equilibrium, this would be this factor would be 0, but that is not the case here. So this is the first evolution of the ground state. Then we can use evolution, we can write the similar equation for the evolution of the first excited state. So for that we have, this is the recombination coefficient to only the first excited state, so to only n equals to 2 state, times the number density of electrons and number density of protons. Number of electrons and number of protons, these are not number densities, because number density will be a function of redshift, so we are just writing numbers. And this is beta 2, so this is the ionization from this state. And finally, we will also need to take care of the transition rate from the first excited state to the ground state, which is this. So this is the rate equation for the first excited state. Now, we are making an assumption here that during the recombination, this value remains constant. N2 remains constant, so this is 0. That whatever transition takes place.
What was beta 2 actually? I forgot what I can. Yes.
Yeah, no, beta 2 is the rate of ionization. So this is the ionization from n equals 2 to continuum, and this is the recombination. Is that fine?
Yes.
Okay. So look, you can think of it this way, that this is, if you want to see the number of particles which are coming in the first excited state, they enter this first excited state through recombination. So this recombination depends on the recombination coefficient for the first excited state, and the number density of number of electrons and the number of protons. And the particles which are leaving this state, they can leave in two ways. They can either go get ionized. So this is the ionization rate from the first excited state. So ionization from n equals to 2 state, and or they can get de-excited. So this is the de-excitation factor here. So these are the two ways in which it leaves the state, and this is the one way in which it enters the state. And what we are going to assume here is the quasi-stationary evolution, that during this process of recombination, only the number of continuum atoms are changing, basically number of electrons and protons is changing, and the number of uh, ground state atoms is changing. So basically there is a net flow of continuum to ground state, but in between this state remains in equilibrium. So there is this is just sort of catalyst state, it remains in equilibrium. So we are just assuming the rate of change of that state to be 0. Now we can put in these values in this equation and we can solve for it. So basically we have Ne P alpha 2 N2, and we will use this equation. So this is A total times this and this is equal to 0. So this is the assumptions that we have. This is, sorry, electron. And we solve it for the N2. So keeping the terms with N2 on one side, we have okay. Is that fine? So basically, N2 is going to be the ratio of these two. So just let me still write down. Is that fine? Am I? If I make any mistakes, just let me know. Okay. So fine. So that is the value of N2 that we put. And now that we can use this value of N2 in um, this equation to get basically expression for N1, this thing. No, okay, sorry. We can use this value put here to get the expression for this. So basically we have this is equal to A total times.
So to solve these two differential equation, we assume that dn2 by dt is 0, okay, and then
Yeah.
we are calculating n1 for using n2.
Yes.
So are there any validation, like any result which validate our assumption, or like we are just assuming that it's 0, or is it physics behind it?
Uh, I'm okay. So this is basically an approximate results which they use for getting an approximate answer. But they have also done, say for example, you if you can take effect of higher level transitions and actually calculate this rate levels, and they have done very precise calculations for all of this. So, say, for example, you can see rec fast or CMB fast. Those are the codes which do these calculations, and even doing very precise calculations, it gives this answer. It says that this answer is correct. This equilibrium only breaks down towards the end of recombination, and at that time, yeah, you need to have a little more precise calculations. So this is an approximation which holds correct for like most of the process of recombination, and you can probably do these calculations better numerically without taking this assumption, and it will still give you the same answer. So it is an approximation which you use from the numerical values.
Okay, got it. Understood.
So okay, yeah, I should. So basically you can solve it for this, and I if I written this correct. Yeah, so if you solve it, I'm this is the expression which you get for this the rate of number of particles which are coming into the ground state. Now what you notice here is that this is the recombination rate to the first excited state, and this is the ionization rate if they are in Boltzmann equilibrium. However, so basically, if you ignore this factor, you can simply say that the number of atoms which are arriving in this is just determined by these two processes, that recombination here and the ionization from here. However, there is this factor which comes from the rate of transition of from first excited state to the ground state, and this so this is basically a factor, and this is the inhibition factor. This is called the inhibition factor. That if these processes were taking in vacuum, in that case, this would be this factor would go away, and you can have the recombination to be very fast, much faster than what actually happens, because the repeated scattering of Lyman alpha can be ignored, say for example. So this is the factor that turns up because of these processes. So that is the inhibition factor. And so this is how you can calculate the approximate value of approximate evolutions of the number of particles in the ground state. Now,
Hello,
this,
sorry. Can you please explain the inhibition factor? I didn't get it. What exactly it is?
yeah, okay. So for example, if okay, so for example, if say for example this is repeated scattering, if say for example the number density of particles is very small, in that case what you will have is this the repeated scattering of Lyman alpha can be probably ignored. In which case this the rate of transition from here to here is much faster than the rate of transition from here to here, which means that all the photons which arrive at the first excited state will definitely transition to the ground state. However, this inhibition is the factor which turns up, which says that, which takes into account that that is not always the case. That whatever recombination takes place to the first excited state, a fraction of it only will get transition to the ground state, and the rest of the fraction will get excited again, because the transition to the ground state, rate of the transition to the ground state is not large enough. So if this A total was much larger than the rate of ionization from the first excited state, then you can ignore this effect, ignore this factor, and you get this 1. So basically everything that turns up to the first excited state gets then transition to the ground state. So that is the inhibition factor. Now, does it make sense now?
Yeah. Thank you.
Okay. Yeah, thanks for questions. Like, keep asking. So this ionization rate can be calculated from the recombination rate using this ionization equation. So for this, at least this process, we are assuming that they are in equilibrium using the ionization equation. But this is basically just the 3-level atom that you have taken only the continuum, then there is first excited state, and then there is ground state. You can also take into account the effect of intermediate states, the higher states. Or you can do a trick in which you can take effect of all this in just these two values. So instead of writing beta 2, which is the ionization from first excited state, you can write that as the equivalent ionization from all the states, and instead of the recombination to the first excited state, you can write that as a recombination to all the states. So that is equal to this case B recombination coefficient. So if you do that, then in that case, it's still we are using just 3 number densities. So this is a kind of an 3-level atom, but the rates which we are using is not just this 3-level rates. It also takes into account the higher level. So this is an effective 3-level atom, and this gives result which are like just a few percent different from what higher transitions, if you actually took into account all the number densities of higher transitions and calculated that. So that is the effective 3-level atom. And okay, so I'll wait here if anybody has any questions.
Hello, I'm sorry, but I don't know whether I missed. You basically calculate dN1 by dt using N2 that you have calculated, right?
Yes.
So in the final result, after in the bracket, how do you get beta 2 N1? Like you substitute N2, right?
Yeah.
So when you substitute to dN1 by dt, did I miss something? How would you get that beta 2 here? Because,
okay, this one.
yeah.
Yeah, okay, let me find where I was doing that. Okay, So this was where this is where I made the,
Yeah.
yeah. So this is the A total,
Yes.
this factor, this
Yes.
by this factor, and this is the N2, that's this factor
Mhm.
minus this. So basically you can now again write and take out the values of n1 separate, so they have n total by, so okay, let me just write this as C to save
Mhm.
space.
Yeah.
So this is just C, and you have NE, NP,
Yeah.
alpha 2
Yeah.
plus this is the A total n1, and let's take the n1 separate also. So now this is also a function of n1, so we have
And one, two.
n1 times here C A
Mhm.
total exponential,
Yeah.
fine,
Yeah.
and this one
Okay. Yeah.
is n1 is already taken
A
care of, so
total
this is A
exponential.
total.
Yeah. C also. You are considering.
Okay, so now wait, yeah, okay, so we have exponential also common and A total also common, so we have C minus, I guess, 1, right? And that is equal to, this was the C, so C minus 1 is, C equals A beta 2 plus A. So C minus 1 is,
A beta. Mm-hmm. Okay.
so you have
Minus.
beta 2
Mhm.
plus A, and putting that here,
Yeah.
instead
Mhm.
of this you have
Beta 2 by, yeah.
yeah, negative beta 2 by beta 2 plus A total, and this factor is again C,
Mhm.
so
Yeah.
you have this.
Yeah. 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 Got it. Okay. Sorry. Yeah. Thank you.
Yeah, sure. No problem. So is this fine? Any more questions? Okay. So then we have, this is the recombination plot which Shiva has already shown. So this is the, let me use different, and this is the first recombination of hydrogen. So this is helium. So this is when the helium from second excited state went to the first excited state. And this is the second recombination of helium. So in this case, it went to the neutral helium, and this is basically the hydrogen, ionized hydrogen went to the neutral hydrogen. So I want you to calculate these redshifts, approximate redshifts, using Saha ionization equation, which I had shown earlier, and it is also in the notes. So it will not be maybe completely precise, but they will, ionization equation is way more valid for the recombination of helium than it is for the recombination of hydrogen, because recombination of hydrogen has other complications. So finally, this, by the way, this is this recombination does not fall as the what ionization would predict, something like this, which would be the basically which would be the exponential decrease what ionization predicts, but it has this tapering off. So there is something, some fraction of the residual ionization which remains till very low redshift, and Shiv has already talked about it. It has very important implications for the 21 centimeter signal. The scale of the 21 centimeter signal that you want to um, uh, observe depends very severely on this value, and we get very precise values of this from the numerical simulations. But just to get some idea, we can do order of magnitude calculations in this tutorial. So let me do that. So this is the residual ionization fraction. So basically residual ionization fraction, what processes takes place over here? Why do we have this residual ionization? Is because this is the recombination rate. It starts becoming equal to the expansion rate, which means that now the universe suddenly starts expanding fast enough that the recombination, the process of electrons and protons coming together is and forming a hydrogen atom is slower than the expansion of the universe, which means that the fraction neutral fraction the ionized fraction almost freezes out. So we have this rate, which is the recombination rate. Basically this is the case 2 recombination coefficient. Case 2 recombination coefficient takes into account the recombination to all the higher states other than the first, the ground state, because as we saw that the recombination to ground state gives almost negligible result. So this is the recombination to the, so this is the recombination rate, which I have calculated put here. And we can compare this to the Hubble expansion rate. So we can compare this to h of z, which is basically for the matter-dominated universe. So we will always be using this matter-dominated approximation. And so we can calculate this number density. Okay, so basically here, this is the number density of electrons. And this number density of electrons can be expanded as the ionization fraction, which we want to calculate, times the number density of hydrogen, the total number density of hydrogen. And that is a function of redshift. So basically here there are two functions of redshift, and we can calculate xe as a function of redshift. So what we have is comparing these two things, that this is 3 by 2 times this. By the way, there will be another redshift factor from here. So we can write this temperature. Basically, this temperature is the, we can write compare for now as the CMB temperature. So let's write that as this times 0.8 into 1 plus Z 0.8 times this. Sorry. Yeah. So this. Am I missing anything? No. So we can simplify this. Let's first count all the factors of redshift. So we have minus 3 by 2, these two, plus 0.8 times and this factor. Which is 0. So there are all these values. You can put and calculate them now if you want. I'll wait for a few minutes. If you have a calculator, just put all these values and let's derive the residual ionization fraction. Mind that this is just order of magnitude approximation that we have simply equated the recombination rate to the Hubble expansion rate and not done anything more sophisticated, but it still gives the correct order of magnitude. So if you want, please calculate and somebody tell me what's the value you get. You can simply put the value of hydrogen, Hubble constant here, and not replace the h value and then use this combination instead. So this combination is what generally turns out. Did anyone do this calculation? I think the time is over, so let's just finish this residual ionization fraction calculation and then I'll stop.
Yeah, they can, thank you. And they can also calculate and interact in the Slack channel. Yeah. Please come up with your answer and put it in the Slack channel. I hope you are there, right? You can.
Yeah.
Yeah. So yeah, you can check the answer.
Yeah. Please.
Yeah, so
Also, like if you find any problem with the notes or if there is any errors, and then please let me know. I might send you an updated version because I found a couple of errors, and but just let me know if you have any questions, any doubts, something is not making sense, something is maybe more explanation is needed for something, or something is downright just wrong. Please let me know. We can discuss that on Slack, or we can discuss that over the tutorials tomorrow. So please take a look. Okay.
yeah, thank you. And yeah, so if you have any further question, you can just ask quickly right now.
So this the redshift value. So this XC will be calculated in the. Will it contain the term of Z, or will the redshift get cancelled away?
No, redshift should be there. So I already calculated the redshift fraction, and that is around, like, this redshift fraction remains. So you will have some redshift fraction, but this rest of the things will get calculated. So what basically we want to do eventually is, we want, given the redshift, we want to calculate what is the XC. So redshift factor will still remain. Calculate it in terms of redshift. Then. Fine.
Okay, so please come up with your answer in the Slack channel. Yeah.
Yeah.
Yeah, we are running out of time. So yeah, if you have still any urgent question, you can just ask, or we can wrap up.
So, ma'am, we are calculating this XC as a function of Z.
Yes.
Okay, so one thing I missed, I think, we are putting this R, recombination rate is equal to Hubble constant.
Yes.
Okay, thank you.
So no, basically this is, I mean, if you do numerical calculations, you can get very precise value of XE, but this is just for our understanding that why XE is not exactly zero, why there is not complete recombination, why something remained. For that, the logic is this, that the recombination rate becomes equal to the Hubble expansion rate. So we can do this an order of magnitude calculation. Okay.
Okay, I don't see any further hands. So let us thank Janakee again, and yeah, she will continue this